Okay, let's try part B. Where do you need to put a target that is 1.45 meters above the ground in order to hit it if you aim 30 degrees above the horizontal? Sounds complicated. Let's see what we can do. Okay, so we're down here now. We're going to try doing this part B. And as usual, we're going to start with a picture. So I'm firing an arrow, but this time I'm firing it 30 degrees. So I'm going to go ahead and draw a 30-degree angle. I'm also going to remind myself that this distance is 1.45 meters above the ground. I'm going to go all the way over here, and here's a target that I want to hit. And this target is also where I want to hit anyway. Let's go ahead and move our target. Our target is also 1.45 meters above the ground. So if we think about it that way, it sounds like a simplifying way to do this problem is to realize that we're firing an arrow as if it was from ground level in a sense, and hitting the ground. Okay, so we're both launching and hitting at the same height. Now, how do you do a problem like this? Well, this one actually has to be broken down into the two components of the motion of the arrow. So I can think of the vertical component and the horizontal component. Now, the way I can do that here is I can call this an initial velocity. But if this is an angle theta, then I can think of that initial velocity as broken into an initial velocity in the x direction, but also an initial velocity in the y direction. So this arrow plus this arrow is the same as this arrow. Okay? That's how you can add vectors. So I can write that the VIY is going to be the same as the VI times the sine of 30 degrees. Well, the sine of the angle, I guess, I should say, because I'm being a little more general right now. And the initial velocity in the x direction is VI times cosine of theta. This is a pretty advanced problem here, so let's see what we can do. I realized, let's say, if I knew how long the arrow is in the air, then I could take this speed here, this Vix, this initial velocity in the x direction, and just multiply by the time, and I would get the range. I'd get the total distance that I'd need to go to hit that target just right. So I'd like to get the time that it's in the air. So what I'm going to do is use this relationship to try to figure out how long the thing is in the air. So again, I can sort of write down whatever it is I think I know. So I could do something, for example, like this. I could say that the height of the object is going to be a half gt squared, right, plus the initial velocity in the y direction in this case times time, plus the initial height. And I could say, well, is there anything useful I can get out of this? Well, the initial height, right, would between the initial height and how high it gets, let's say up to the very, very top. There's different ways I can do this problem, actually. I could either think of the initial height and the, well, what the heck, yeah, let's just think of this as the final height's 1.45, and so is the initial height 1.45. So if I do that, these two things cancel, and I would get then 0, and I can factor out a t here. It's going to be a half gt plus VIY, right? Now, this looks kind of good. It says that when t is 0, this works, and that just tells you that the arrow is at the 1.45 meter level when time is 0, which is sort of what made sense. And then I could solve for this other option for t. So why don't I do that? I have 1/2 gt plus VIY. If that's 0, then that will be the time at which I hit the target. Now, that may not be super obvious to you right away, but think about that for a little bit. So I can solve for t here, and I can get t must be 2 times VIY over little g with a minus sign. And now that's going to be 2 times the VI times the sine of the angle, right, over, in this case, minus 10. I guess, is that right? Oh, sorry, there's a minus sign, minus over 10 meters per second squared. Now, if I think about what have I got here, All this looks very confusing, of course, right? But in my problem, I know theta is 30 degrees. And I know that the initial speed, vi, is something that I got in the previous part of the problem. So that was up here somewhere. I got this 22.5 meters per second. So I imagine that I know those two things. I know the vi and I know the initial theta. So I know viy. I know I'm going to be able to figure out viy. So so that'll give me the time. Once I have the time, I multiply that time by this vix, and I'll get that distance. So basically all the physics is already over right now. So let me just go ahead and do this for you. So I've got time that it's in the air. It's going to be the 2 times the vi that we figured out in the last problem. And the vi we figured out in the last problem, I think, was 22.5 meters a second. Is that right? Let's see. Or at least that's what I estimated it to be anyway. 22.5 meters per second times the sine of 30 degrees. Now the sine of 30 degrees is 1/2. So sine of 30 degrees, that happens to be equal to 1/2. So this is actually going to cancel with that 2 right there. And I'm going to divide by 10 meters per second squared. And finally I get something like 2.25. It looks like I'm going to get about 2.25 seconds. So that's pretty cool. Now notice that 2.25 seconds is more time than we got over here when we just fired the arrow horizontally. And that's because the arrow is able to go up in the air too, right? So okay, so far we're looking pretty good. I need to know that the range then, okay, the range, where that range is going to be this speed, right? So that range is this distance, how far it goes. It's going to be the speed times that time. So here I'm going to have vi times the cosine of 30 degrees and times this time up here, the 2.25 seconds. So this is the speed in the horizontal direction times the time that it's in the air. And this is going to give me something like, what was it, that 2.25, and the cosine of 30 degrees is the same as it turns out, √3/2, and I think that's something like about 0.86 or something. I may have that wrong, but I think it's about 0.86. Then I multiply by my 2.25, and I'm going to get an answer in meters because I've only used standard units. And whatever this looks like, 0.86 times 2.25, I don't know, if I had to make a guess and get a little bit lazy, I'd say that's about 2, so I'm going to do 2 times 22.5, that's about 45 meters. So I'm going to finally guess about 45 meters. Now I may be, chances are I'm off by a little bit, but I wouldn't expect myself to be off by too much. You can calculate it yourself, and that's how we can do a pretty complex, pretty sophisticated problem here, and definitely a beyond level for our class, but some of you might want to try to understand the physics behind that. What assumptions did we make? Well, we assumed that the air didn't matter. It was the primary assumption. We assumed that we could take all these accelerations and say they were constant. We imagined that the acceleration in the horizontal direction was 0, so it didn't speed up or slow down as it moved horizontally. That way we could do speed times time is distance and use a single speed, which is to say this single speed that never changed. Okay, so good luck. Go back through the video again if you need to.